Sauce here. This is a video lesson on logarithms. Logarithms are not mysterious. They're just the inverse operation to an exponential. And inverse operations are something that we've been working with for many years in algebra. For example, if we had the equation x plus 2 is equal to 1, we need to undo the addition of 2 to get x by itself. The inverse operation to addition is subtraction. So if we subtract 2 from both sides, they will cancel out, leaving x by itself. We can evaluate the right side. Addition and subtraction are inverses of each other because they cancel each other out, or they undo each other. Another example of inverse operations, 2x is equal to 1. We have multiplication here, and we know that the inverse of multiplication is division. So if we divide both sides by the same amount, it cancels out, leaving x. Multiplication and division are inverses of each other. We have another pair of inverse operations when we deal with powers. X squared is equal to 1 means that we have to undo the square in order to get x by itself. The inverse of a power, where the base is the variable, is a root. And that's true for any power. So the nth power of x has an inverse nth root of x. They undo each other. To undo the squaring, I need to square root both sides. That leaves x by itself. But there are powers. Power has two components. It has a base and an exponent. And in this power, the base is the variable. But what if I was to draw a power whose variable is in the exponent position? This is a very different kind of expression. This is an exponential expression. And if we had an equation in which we wanted to solve for the variable, where the variable was in the exponent position, we have to undo the power base. So what do I do to both sides to undo this power base? That's what the logarithm is. It's the inverse of a power base. We could literally call this power base 2. And what we need to do to both sides is the log base 2 to undo it. We show the work like this. We're taking the log base 2 of the power base 2, and we're going to do the same thing to both sides, because when we do, the log base 2 and the power base 2 cancel out. They're inverse operations, leaving x by itself. And it's no longer an exponent because its base has been taken away or undone. On the other side, we might need a calculator if we're not familiar with the log base 2 of 1. What does that mean? Well, in the original equation, what we were looking for is the power of 2 that will equal 1. And in this case, we're familiar with when we have a 0 exponent, then it doesn't matter what the base is, it will evaluate to 1. So we know what the log base 2 of 1 is. In this case, it's 0. Most often, we'll need a calculator in order to evaluate something like this, a logarithm. So we have another pair of inverse operations. When our power is exponential, which means that the variable is in the exponent position, the inverse operation is the log of the same base. These are operations that undo each other. Let's give another example. What if we have an equation like this? Log base 4 of x is equal to 2. And we're trying to get x by itself, which means that we have to undo log base 4. What's the inverse of log base 4? Well, here we have the two inverses of each other. If I start with a log base 4 of x, the inverse of that is going to be a power whose base is 4. So to get x by itself, I need to power base 4 both sides. That'll undo the log base 4. What does that look like if I was to show my work? Well, if I'm looking for a power whose base is 4, and I put a 4 there, then what I've drawn is a power where what I had previously, log base 4 of x, is now in the exponent position of the power whose base is 4. And what I do to one side, I must do to the other. It's a little unusual, but we can do that. We can power base 4 both sides. And when we do, the log base 4 and the power base 4 cancel out, leaving x. And on the other side, I have to evaluate what 4 to the second power is. That's not too difficult. It's 16. Logarithms are not mysterious. They're just the inverse of exponentials. And we need them just as we need all of the previous inverse operations in order to solve equations.